a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Space Shuttle Challenger disaster. On January 28, 1986, the NASA Shuttle Orbiter mission STS-51 liters and the 10th flight of broke apart 73 seconds into its flight, killing all 7 crew members, which consisted of 5 NASA astronauts and 2 payload specialists. The spacecraft disintegrated over the Atlantic Ocean, off the coast of Cape Canaveral, Florida, at 11:39 EST. The disintegration of the vehicle began after an O-ring seal in its right solid rocket booster failed at liftoff. The O-ring was not designed to fly under unusually cold conditions as in this launch. Its failure caused a breach in the SRB joint it sealed, allowing pressurized burning gas from within the solid rocket motor to reach the outside and impinge upon the adjacent SRB aft field joint attachment hardware and external fuel tank. This led to the separation of the right-hand SRB's aft field joint attachment and the structural failure of the external tank. Aerodynamic forces broke up the orbiter. The crew compartment and many other vehicle fragments were eventually recovered from the ocean floor after a lengthy search and recovery operation. The exact timing of the death of the crew is unknown. Several crew members are known to have survived the initial breakup of the spacecraft. The shuttle had no escape system, and the impact of the crew compartment with the ocean surface was too violent to be survivable. The disaster resulted in a 32-month hiatus in the shuttle program and the formation of the Rogers Commission, a special commission appointed by United States President Ronald Reagan to investigate the accident. The Rogers Commission found NASA's organizational culture and decision-making processes had been key contributing factors to the accident, with the agency violating its own safety rules. NASA managers had known since 1977 that contractor Morton Thiokol's design of the SRBs contained a potentially catastrophic flaw in the O-rings, but they had failed to address this problem properly. NASA managers also disregarded warnings from engineers about the dangers of launching posed by the low temperatures of that morning, and failed to adequately report these technical concerns to their superiors. What the Rogers Commission report did not highlight was that the vehicle was never certified to operate in temperatures that low. The O-rings, as well as many other critical components, had no test data to support any expectation of a successful launch in such conditions. Bob Ebling, from Thiokol, commented, "We are only qualified to 40 degrees. What business does anyone even have thinking about 18 degrees? We're in no man's land." Ken Iliff, a former NASA chief scientist who had worked the Space Shuttle program since its first mission, stated in an official 2004 NASA publication, "Violating a couple of mission rules was the primary cause of the Challenger accident." Robert Villa was one of 2 teacher in space candidates from New Hampshire, and he stated, "The day they finally flew the Shuttle Challenger, I never thought they would, because it was in fact a very cold morning and the shuttle was just not designed to fly under those conditions." As a result of the disaster, the Air Force decided to cancel its plans to use the shuttle for classified military satellite launches from Vandenberg Air Force Base in California, deciding to use the Titan IV instead. Approximately 17% of Americans witnessed the launch live because of the presence of payload specialist Krista McAuliffe, who would have been the first teacher in space. Media coverage of the accident was extensive. One study reported that 85% of Americans surveyed had heard the news within an hour of the accident. The Challenger disaster has been used as a case study in many discussions of engineering safety and workplace ethics. O-ring concerns. Each of the Space Shuttle's 2 solid rocket boosters was constructed of 7 sections, 6 of which were permanently joined in pairs at the factory. For each flight, the 4 resulting segments were then assembled in the Vehicle Assembly Building at Kennedy Space Center, with 3 field joints. The factory joints were sealed with asbestos silica insulation applied over the joint, while each field joint was sealed with 2 rubber O-rings. The seals of all of the SRB joints were required to contain the hot, high-pressure gases produced by the burning solid propellant inside, thus forcing them out of the nozzle at the aft end of each rocket. During the Space Shuttle design process, A McDonnell Douglas report in September 1971 discussed the safety record of solid rockets. While a safe abort was possible after most types of failures, one was especially dangerous: a burn-through by hot gases of the rocket's casing. The report stated that, if burn-through occurs adjacent to liquid hydrogen/oxygen tank or orbiter, timely sensing may not be feasible, and abort not possible, accurately foreshadowing the Challenger accident. Morton Thiokol was the contractor responsible for the construction and maintenance of the shuttle's SRBs. As originally designed by Thiokol, the O-ring joints in the SRBs were supposed to close more tightly due to forces generated at ignition, but a 1977 test showed that when pressurized water was used to simulate the effects of booster combustion, the metal parts bent away from each other, opening a gap through which gases could leak. This phenomenon, known as joint rotation, caused a momentary drop in air pressure. This made it possible for combustion gases to erode the O-rings. In the event of widespread erosion, a flame path could develop, causing the joint to burst, which would have destroyed the booster and the shuttle. Engineers at the Marshall Space Flight Center wrote to the manager of the Solid Rocket Booster Project, George Hardy, on several occasions suggesting that Thiokol's field joint design was unacceptable. For example, one engineer suggested that joint rotation would render the secondary O-ring useless, but Hardy did not forward these memos to Thiokol, and the field joints were accepted for flight in 1980. Evidence of serious O-ring erosion was present as early as the second Space Shuttle mission, STS-2, which was flown by Columbia. Contrary to NASA regulations, the Marshall Center did not report this problem to senior management at NASA, but opted to keep the problem within their reporting channels with Thiokol. Even after the O-rings were redesignated as Criticality 1, meaning that their failure would result in the destruction of the orbiter, no one at Marshall suggested that the shuttles be grounded until the flaw could be fixed. After the 1984 launch of STS-41D, flown by Discovery, the first occurrence of hot gas blow-by was discovered beyond the primary O-ring. In the post-flight analysis, Thiokol engineers found that the amount of blow-by was relatively small and had not impinged upon the secondary O-ring, and concluded that, for future flights, the damage was an acceptable risk. However, after the Challenger disaster, Thiokol engineer Brian Russell identified this event as the first big red flag regarding O-ring safety. By 1985, with 7 of 9 shuttle launches that year using boosters displaying O-ring erosion and/or hot gas blow-by, Marshall and Thiokol realized that they had a potentially catastrophic problem on their hands. Perhaps most concerning was the launch of STS-51B in April 1985, flown by Challenger, in which the worst O-ring damage to date was discovered in post-flight analysis. The primary O-ring of the left nozzle had been eroded so extensively that it had failed to seal, and, for the first time, hot gases had eroded the secondary O-ring. They began the process of redesigning the joint, with 3 inches of additional steel around the tang. This tang would grip the inner face of the joint and prevent it from rotating. They did not call for a halt to shuttle flights until the joints could be redesigned, but rather treated the problem as an acceptable flight risk. For example, Lawrence Malloy, Marshall's manager for the SRB project since 1982, issued and waived launch constraints for 6 consecutive flights. Thiokol even went as far as to persuade NASA to declare the O-ring problem closed. Donald Kutina, a member of the Rogers Commission, later likened this situation to an airline permitting one of its planes to continue to fly despite evidence that one of its wings was about to fall off. Delays. Challenger was originally set to launch from Cape in Florida at 14:42 Eastern Standard Time on January 22, 1986. Delays in the previous mission, STS-61C, caused the launch date to be moved to January 23 and then to January 24. The launch was then rescheduled to January 25 due to bad weather at the transoceanic abort landing site in Dakar, Senegal. NASA decided to use Casablanca as the trial site, but, because it was not equipped for night landings, the launch had to be moved to the morning. Predictions of unacceptable weather at Cape on January 26 caused the launch to be rescheduled for 9:37 EST on January 27. The launch was delayed the next day, due to problems with the exterior access hatch. First, one of the micro-switch indicators, used to verify that the hatch was safely locked, malfunctioned. Then, a stripped bolt prevented the close-out crew from removing a closing fixture from the orbiter's hatch. By the time repair personnel had sawed the fixture off, crosswinds at the shuttle landing facility exceeded the limits for a return to launch site abort. While the crew waited for winds to die down, the launch window expired, forcing yet another scrub. Thiokol-NASA conference call. Forecasts for January 28 predicted an unusually cold morning, with temperatures close to -1°C, the minimum temperature permitted for launch. The shuttle was never certified to operate in temperatures that low. The O-rings, as well as many other critical components, had no test data to support any expectation of a successful launch in such conditions. By mid-1985, Thiokol engineers worried that others did not share their concerns about low temperatures' effects on the boosters. Bob Ebeling in October 1985 wrote a memo, titled, "Help," so others would read it, of concerns regarding low temperatures and O-rings. After the weather forecast, NASA personnel remembered Thiokol's warnings and contacted the company. When a Thiokol manager asked Ebeling about the possibility of a launch at 18 degrees, he answered, "We are only qualified to 40 degrees. What business does anyone even have thinking about 18 degrees? We're in no man's land." After his team agreed that a launch risked disaster, Thiokol immediately called NASA recommending a postponement until temperatures rose in the afternoon. NASA manager Judd Lovingood responded that Thiokol could not make the recommendation without providing a safe temperature. The company prepared for a teleconference 2 hours later, during which it would have to justify a no-launch recommendation. At the teleconference on the evening of January 27, Thiokol engineers and managers discussed the weather conditions with NASA managers from a Kennedy Space Center and Marshall Space Flight Center. Several engineers reiterated their concerns about the effect of low temperatures on the resilience of the rubber O-rings that seal the joints of the SRBs, and recommended a launch postponement. They argued that they did not have enough data to determine whether the joints would properly seal if the O-rings were colder than 12°C. This was an important consideration, since the SRB O-rings had been designated as a criticality 1 component, meaning that there was no backup if both the primary and secondary O-rings failed, and their failure could destroy the orbiter and kill its crew. Thiokol management initially supported its engineers' recommendation to postpone the launch, but NASA staff opposed a delay. During the conference call, Hardy told Thiokol, "I am appalled. I am appalled by your recommendation." Malloy said, "My God, Thiokol, when do you want me to launch?" Next April. NASA believed that Thiokol's hastily prepared presentation's quality was too poor to support such a statement on flight safety. One argument by NASA personnel contesting Thiokol's concerns was that if the primary O-ring failed, the secondary O-ring would still seal. This was unproven, and was in any case an argument that did not apply to a criticality 1 component. As astronaut Sally Ride stated when questioning NASA managers before the Rogers Commission, "It is forbidden to rely on a backup for a criticality 1 component." NASA claimed that it did not know of Thiokol's earlier concerns about the effects of the cold on the O-rings, and did not understand that Rockwell International, the shuttle's prime contractor, viewed the large amount of ice present on the pad as a constraint to launch. For reasons that are unclear, Thiokol management reversed itself and recommended that the launch proceed as scheduled. NASA did not ask why. Ebeling told his wife that night that Challenger would blow up. Ken Iliff, a former NASA chief scientist who had worked on the Space Shuttle program since its first mission, stated in 2004, violating a couple of mission rules was the primary cause of the Challenger accident. Ice. The Thiokol engineers had also argued that the low overnight temperatures would almost certainly result in SRB temperatures below their red line of 4°C. Ice had accumulated all over the launch pad, raising concerns that ice could damage the shuttle upon liftoff. The Kennedy ice team inadvertently pointed an infrared camera at the aft field joint of the right SRB and found the temperature to be only -13°C. This was believed to be the result of supercooled air blowing on the joint from the liquid oxygen tank vent. It was much lower than the air temperature and far below the design specifications for the O-rings. The low reading was later determined to be erroneous. the error caused by not following the temperature probe manufacturer's instructions. Tests and adjusted calculations later confirmed that the temperature of the joint was not substantially different from the ambient temperature. The temperature on the day of the launch was far lower than had been the case with previous launches, below freezing at -2.22. Previously, the coldest launch had been at 12°C. Although the ice team had worked through the night removing ice, engineers at Rockwell still expressed concern. Rockwell engineers watching the pad from their headquarters in Downey, California, were horrified when they saw the amount of ice. They feared that, during launch, ice might be shaken loose and strike the shuttle's thermal protection tiles, possibly due to the aspiration induced by the jet of exhaust gas from the SRBs. Rocco Petroni, the head of Rockwell's Space Transportation Division, and his colleagues viewed this situation as a launch constraint, and told Rockwell's managers at the Cape that Rockwell could not support a launch. Rockwell's managers at the Cape voiced their concerns in a manner that led Houston-based mission manager Arnold Aldrich to go ahead with the launch. Aldrich decided to postpone the shuttle launch by an hour to give the ice team time to perform another inspection. After that last inspection, during which the ice appeared to be melting, Challenger was cleared to launch at 11:38 a.m. EST. Liftoff and initial ascent. The following account of the accident is derived from real-time telemetry data and photographic analysis, as well as from transcripts of air-to-ground and mission control voice communications. All times are given in seconds after launch and correspond to the telemetry time codes from the closest instrumented event to each described event. The Space Shuttle main engines were ignited at T6.6 seconds. The SSMEs were liquid-fueled and could be safely shut down until the solid rocket boosters ignited at T0, and the hold-down bolts were released with explosives, freeing the vehicle from the pad. At liftoff, the three SSMEs were at 100% of their original rated performance, and began throttling up to 104% under computer control. With the first vertical motion of the vehicle, the gaseous hydrogen vent arm retracted from the external tank, but failed to latch back. Review of film shot by pad cameras showed that the arm did not recontact the vehicle, and thus it was ruled out as a contributing factor in the accident. The post-launch inspection of the pad also revealed that kick springs on 4 of the hold-down bolts were missing, but they were similarly ruled out as a possible cause. Later review of launch film showed that at T+0.678, strong puffs of dark gray smoke were emitted from the right-hand SRB near the aft strut that attached the booster to the ET. The last smoke puff occurred at about T+2.733. The last view of smoke around the strut was at T+3.375. It was later determined that these smoke puffs were caused by the opening and closing of the aft field joint of the right-hand SRB. The booster's casing had ballooned under the stress of ignition. As a result of this ballooning, the metal parts of the casing bent away from each other, opening a gap through which hot gases, above 2,760 C, leaked. This had occurred in previous launches, but each time the primary O-ring had shifted out of its groove and formed a seal. Although the SRB was not designed to function this way, it appeared to work well enough, and Morton Thiokol changed the design specs to accommodate this process, known as extrusion. While extrusion was taking place, hot gases leaked past, damaging the O-rings until a seal was made. Investigations by Morton Thiokol engineers determined that the amount of damage to the O-rings was directly related to the time it took for extrusion to occur, and that cold weather, by causing the O-rings to harden, lengthened the time of extrusion. On the morning of the disaster, the primary O-ring had become so hard due to the cold that it could not seal in time. The temperature had dropped below the glass transition temperature of the O-rings. Above the glass transition temperature, the O-rings display properties of elasticity and flexibility, while below the glass transition temperature, they become rigid and brittle. The secondary O-ring was not in its seated position due to the metal bending. There was now no barrier to the gases, and both O-rings were vaporized across 70 degrees of arc. Aluminum oxides from the burnt solid propellant sealed the damaged joint, temporarily replacing the O-ring seal before flame passed through the joint. As the vehicle cleared the tower, the SSMEs were operating at 104% of their rated maximum thrust. and control switched from the Launch Control Center at Kennedy to the Mission Control Center at Johnson Space Center in Houston, Texas. To prevent aerodynamic forces from structurally overloading the orbiter, at T+28 the SSMEs began throttling down to limit the velocity of the shuttle in the dense lower atmosphere. Per normal operating procedure, at T+35.379, the SSMEs throttled back further to the planned 65%. 5 seconds later, at about 19,000 foot, Challenger passed through Mach 1. At T+51.860, the SSMEs began throttling back up to 104% as the vehicle passed beyond Max Q, the period of maximum aerodynamic pressure on the vehicle. Brought to you by WikiVidi documentaries. Would you like to know more?